Okay, so carrying straight on, this is part 2, just so that it doesn't take me forever to upload them and it's insanely long. So this is the GCSE stuff that I've just been through. If you haven't watched that, please do. I do think it's really useful to get an understanding of the GCSE content before we move on to the A-level content. Now, at A-level, we apply basically more maths to that. GCSE, we just sort of say, well, yeah, we induce a potential difference. And then at A-level, we actually start talking about EMF instead, because at A-level, you know the difference between terminal PD and EMF. EMF is the energy, the chemical energy transferred to electrical energy per unit charge in the battery when you move a charge the whole way around the circuit. And the reason why EMF is not the same as potential difference is potential difference, or terminal PD, the across the battery, is always lower than EMF because of the internal resistance of the battery, right? So we're now going to talk about EMF rather than potential difference, because we know that there is some of the energy generated by the battery, some of the EMF is lost inside the battery, the lost volts across the internal resistance. And so this really is about generating EMF rather than potential difference. But essentially, it's the same thing. Everything I spoke about in the GCSE one, when I use potential difference, it's just basically change it for EMF, because it's a slightly better way of describing what we're actually producing inside the battery. Now, we also go into more detail about defining this idea of magnetic flux density, or the magnetic field. Instead of saying cutting through lines, we talk about like flux linkage and flux. Now, the magnetic flux density, or the strength of the magnetic field, is still B, right? It's still given as B, but we define this new term called magnetic flux. And magnetic flux is a way of describing how many magnetic field lines we've actually cut through. So, I mean, if I sort of give you an example, if I move this wire the whole way down inside through here, then there's an area there of magnetic field lines that I've cut through, right? And if I multiply by the area by the strength of the magnetic field, I'm going to get a measure of how many field lines I've cut through. If this is sort of like this, right? If this was much longer, I could cut through, my area would be bigger. I'd be cutting through more field lines. I'd be inducing more PD, right? If B was greater, so to increase B, it would be me going ahead and adding loads more yellow lines, right? And that's the magnetic field strength, or the magnetic flux density. Now, the magnetic flux is given this symbol phi here, this little circle with a line through it, and that's BA. So it's the magnetic field strength multiplied by the area that you've cut through, and it basically gives you a measure of how many yellow field lines you have actually cut through, which is going to be relative to your EMF produced, proportional to the EMF produced. Then there's this term flux linkage, or N phi is BAN, right? And in this case, it's just if we have like 3 turns on the coil and we cut it through, or if I'm cutting two wires through, I'm going to get double the EMF produced. So it's just like basically multiplying by the number of coils of wire you have, or multiplying by the amount of wire you have. And the N just goes on both sides. A weird equation, I suppose, if you think about it. Now, then we get this other equation for a rotating rectangular coil. We get N phi is BAN cos theta. So the idea that actually this is when we're cutting perpendicular to the field lines. So if I try and cut the field lines like this, I'm not actually cutting any, but if I cut them down like that, I'm going to cut through. So it always needs to be perpendicular. Now this angle here, this theta, is slightly tricky, right? So this theta appears, it's the angle between the field, so the north-south field lines, and the normal of the plane of the coil, right? I mean, if I show you here, so if this is like, you imagine this is my field here and this is my coil, it's a rectangular coil in this case, I've only got a circle here, it's kind of like that. Now the diagrams they show you are sometimes awful. They show you sort of like straight lines like that from above, and then one from side on. It's really difficult to show these 3D diagrams, and they end up being very confusing, sort of like at weird angles. But this is basically this coil like that, and the idea is that the plane of the coil, so the normal of the coil is coming out like this, so this is the angle. So it's the angle between the field and the normal, right? I always remind myself, because my instinct would be to do like this angle, no, the angle between the coil and the field. That would be the angle that I would want to do if I was just naturally trying to think about it. And I always remind myself that it's not that angle, it's the angle that I'm less likely to use. Yeah. Now, this also, quite often for this, if we're rotating a rectangular coil, sometimes the questions don't require the use of this cos theta. Sometimes the questions just require the use of maximum or minima. And we have to remember that this cos function, the maximum value it can take is 1. So the maximum n phi is going to be when it's cos of 0, which is when it's perpendicular to the plane, and we just get BAN cos of 0 will give us the maximum value. The minimum value is going to be when it's like this, parallel to the plane, and that's going to be AN cos 90. So if I get confused, I can kind of interrogate it, and I think, well, actually, I want it to be maximum when it's like this, because that's going to be cutting through the most, right? This is going to be cutting through the most. This, when it's like this, it really doesn't cut through much. So I want the maximum like this, so that's why I want it to be cos of not 90 to get the maximum, cos of 0, sorry, to get the maximum value, right? So when it's like this, the angle between, when it's like this, the angle between the plane and the perpendicular and the normal to the angle between the magnetic field and the normal is 0. Yeah, so just remember, and then the minimum value is just 0 when you have cos of 90. So these cos features allow us to figure maximums and minimums relatively easily. Right, now, the next one is, and this is required practical 11, where you put the search coil into the magnetic field at different angles and you get a measure of the fact that it's a cos function. Then there's this idea, Faraday's and Lenz's law. So this is then more about how we're going to link this to EMF. So to a certain extent, this is all describing like flux linkage. Why do we care about that? Because this is related to how we generate electricity, which is very, very important for modern life. So Faraday's law is that the idea of the magnitude of the reduced EMF is equal to the rate of change of flux linkage given in this equation. EMF is n change in phi, change in flux linkage, change in phi divided by the time taken to change. Now, this equation as itself is not particularly useful. Quite often, a more useful form of this is EMF is, well, first of all, putting the n on the top here and saying it's BAN, n phi, change in n phi divided by the change in time, or this n phi is equal to BAN. So it's the change in BAN divided by the change in time. And that is a more useful equation, but you kind of get given this and you get given this and you've got to put them together. So you can work out the EMF produced. Now, the other thing that they do sometimes is if we've got a single wire moving through a magnetic field, so like just a straight conductor moving through this magnetic field, the area that the straight conductor cuts through can be given also by the velocity times the length of the straight conductor. So if you imagine, and also they give you these horrible diagrams like this. You've got this straight conductor here, but it just looks like a circle. It's actually a straight conductor, but if you were to draw the magnetic field lines. So this conductor cuts through an area. If it's moving like this distance, it's going to cut through this area of magnetic field lines. And again, you've got to imagine the magnetic field lines are the whole way through this. It's hard to draw diagrams to represent this. Now, this area here, well, if this is the length of the conductor here, right? Now, if the conductor is moving with a velocity v, then we can say that the speed of the velocity is going to be the distance it travels divided by the time taken. This here represents the distance that my wire has travelled. And so this value for area is going to be the length of wire multiplied by the distance it's travelled. Now, a little bit of jiggery-pokery, we can say E, if we say that E is the change in BAN divided by the time taken for that change, right? If I interrogate this section of it here, so area divided by the time taken. Now, the area divided by the time taken, area from this equation here, is equal to the length times the distance it's travelled in the magnetic field. And if I divide that by the time, then I get length, distance divided by time. And this bit here, then, I can sub out for the velocity of the wire. So this old equation here, the area divided by the time is equal to the length times the velocity. and we can sub this in. So you get this like unlock this secret hidden equation that they actually use quite often in the mark schemes. The EMF is equal to the magnetic flux density multiplied by the length of your single wire times the velocity it's moving at. Now, obviously, I'm going to put the N in there because if it was a doubled up wire, that would exist. But this EMF is BLV. It often comes up, and sometimes it is easier to calculate the velocity of something or the average velocity of something. But if it's moving at constant velocity, you can just use BLV. I mean, you could also, though, if you know it's moving at the average velocity and they tell you the time, you can calculate the distance and then work out the area. So I wouldn't say this is like a massively important equation, but it's one of those equations that does give you a bit of a shortcut to it. In general, this here, EMF is BAN, is the most common equation, right? EMF is the rate of change of BAN, is the most common equation. So what's the area, what's the magnetic flux density, and how long did it take for it to cross through that? It's the most common equation that you use. And it's tricky, they don't give you that, they instead give you this one. Now, so for the GCSE, I mentioned about the idea that this induced EMF opposes the change. And I think like when we've got rods moving through magnetic fields that aren't connected to circuits, we can only talk about the PD being induced because there's not going to be a current flowing. But this induced EMF opposes the change causing it, and that's Lenz's law, right? So sometimes it's quoted as a little negative there. But Faraday's law is technically the magnitude of this. And so it doesn't really matter that we put a negative or not in there, because Lenz's law tells us that it opposes the change causing it. Now, the last bit of this, you'll be relieved to know, is this idea of EMF induced in a coil. Right, so this is then back to this diagram, my little model. We have a coil and we're rotating it in this magnetic field, and we want to find out the EMF induced. And this is the equation given for it. So the EMF is BAN omega sine omega t, which we're like, oh, okay, we're back to this idea of angular speed. So omega is the angular speed, and you have to remember, because it's tricky, isn't it, when you're doing electromagnetic induction, you kind of like think, oh, I don't know what that is, and you might have to look back at the equations for omega to find it out. I always think these ones are helpful to remember. So angular speed is the rate of change of angles, but it's also given as the linear speed divided by the radius, or 2 pi times the frequency, or 2 pi over t. And these are kind of useful equations if you can to remember them, because like otherwise you'll keep flipping back, and they rarely will tell you the angular speed. Normally they'll tell you the time period, and then you have to do 2 pi over t and sub it in. Now again, this equation, there's some easy questions that happen with it where they say it's rotating uniformly in a magnetic field. What's the maximum EMF going to be produced? And this sine omega t function helps us out, because the maximum value that can take is 1. So the EMF max for this coil is going to be BAN omega. The minimum is 0. And because this time it's a sine curve rather than a cos, it's going to take the maximum value when omega t is equal to 90 degrees, right? Again, you have to be careful, radians and degrees, because it'll give you radian value, which would be 90 degrees is pi over 2 radians. That took me a long time. Right. And so again, the tricky thing is they give you some tricky diagrams for this that are hard to figure out. So if we've got this is our rotating coil and we're trying to work out what the area is, well, it's going to be this whole area that it's cutting through. So you do the area of the circle. If it was a rectangle, you do the area of a rectangle. It's the area that it's cut through. B, the magnetic flux density, they'd have to give you that, or maybe you're trying to find that if you have the other values. N is the number of turns on a coil, so it might have like 10 turns or whatever like that, and then that is just the angular speed, which you might have to work out from one of these equations. Yeah, it's really tricky. That is pretty much it. If there's any, like, I realize this is a really long video, if there's anything you'd like me to like elaborate on, just send me an email if I teach you, or write it in the comments. I do read them, but I don't post because it feels like kind of like a bordering on social media, and that's not my thing. But just let me know and I can do a video on one particular section of it, because I appreciate this has been quite long, especially as this is part 2. I'm going to try and make one of these every day over half term, over Easter holidays, but forgive me if I don't get time to one day. Thank you.